Hey kids, Mr. Murray here, Mr. Murray's Mathland, and today we're taking a look at some examples of U-substitution for integration. And U-substitution, it's not often necessary, but when it's used, it helps you sort of undo the chain rule, helps you kind of sort out uh, what you're dealing with primarily. So take a look at this. We're trying to integrate 8x cubed times 6x to the fourth minus 7 to the 7th power. And I certainly don't want to expand that to the 7th power just so I can use the power rule on this. So a useful tip for U-substitution is we're going to let something be represented by U. It's just a letter, by the way. It could be any letter, but it tends to be U. And a good tip for that is to let U be the inner expression. That's when the chain rule is used for derivatives, right? When you have something on the inside of a function other than just plain old x, right? You got a composition of functions. So in this case, I'm going to look right here on the inside of that 7th power there. You've got 6x to the fourth minus 7. I'm going to let that be my U value. Okay, now I'm doing this as if it's the first one ever, so I'm going to do this, maybe a little more slowly, and I'll start to take some shortcuts when we get comfortable. Okay, so now, if I'm letting that stand in place of 6x to the fourth minus 7, so I would have now, instead of that, I would have U to the 7th power dx. But here's the thing, if you want to integrate this and you're going to call this U, you need everything to be in terms of U. You want only one variable. So I don't want any x's here, and I definitely don't want dx. I want that to be with respect to U. So I need du. And that's what we do over here. We do a little work on the side here where I have U equals 6x to the fourth minus 7. Now I'm going to take the derivative of that. And when you take the derivative of each side, we're taking it with respect to x. See here how I would normally get dy dx, I'm getting du dx. And on the right side, I have 24x cubed. Okay, so the derivative with respect to x is 24x cubed. Now what I'm going to do is I'm going to multiply both sides by dx, separate those differentials, and now you have that, du is equal to 24x cubed dx, and I'm going to solve for dx. I'm going to basically take this dx out and replace it with what it's equal to. So to do that, I'm going to divide by 24x cubed, and that's going to cancel. And now I'm going to go to this integral here, 8x cubed. This is U to the 7th, and in place of that dx, I'm putting this expression, du over 24x cubed. du over 24x cubed. And notice what's going to happen here is the x cubes are going to cancel out. And that's definitely what you want to happen. There can't be any variable other than u, or whatever variable you're integrating with respect to. And 8/24 while I'm at it reduces to 1/3. So 1/3, you might pull that out in front of the integral because it's a constant coefficient. You might leave it in front of the u to the 7th. It doesn't really matter. But there's what we're dealing with after we do that substitution. And see, now I can integrate that. That's just a basic power rule. So the antiderivative of u to the 7th becomes u to the 8th. And then you divide by that 8, so you get 1/8. There's plus c, because we're doing indefinite integrals again, so we need plus c on the end. And so we get 1/24 u to the 8th. And we are not going to leave our answer in terms of u, because we were letting u kind of stand in place of 6x to the fourth minus 7. And so I substitute that back in, 6x to the fourth minus 7, all to the 8th power, plus c. And there we go. And like always, you can check this by differentiating it, taking its derivative, and you should get right back what you started with here, right? Power rule, 8 times that 1/24th will give you 1/3. This will be dropped down to the 7th power. And then when you multiply by that derivative of the inside, that's where you'll end up with 8x cubed when all is said and done. Okay, so let's just try another couple examples, and we're going to start to polish this process up right here. Take a couple little shortcuts here. Okay, and so notice. All right, so take a look at this one. Looks pretty ugly here, but I've got this quantity, and I've got the 5th root of this quantity. So what should I let u be? I would go to the inside of that 5th root. And usually another kind of rule of thumb, once you get good with these, if you're asking yourself, what am I going to let u be, is you maybe take the more complicated expression, meaning this is 8x to the 4th power. It's a higher exponent than this. And also, if you start to think ahead a step, once you take this thing's derivative, you're going to get an x to the 3rd, and that's going to allow this stuff to cancel out, hopefully. So you get good at this stuff, you can really start to skip a lot of steps, but I'm not going to skip too many. It's only the second example. But I am going to let u stand in place of that 8x to the 4th minus 2x cubed. It's still dx. But here's one shortcut I'm going to take. Off to the side when I do my du over dx, since I'm always going to split up that differential, I'm just going to start taking the derivative with it already separated. So derivative of u, du. Derivative of 8x to the 4th minus 2x cubed, 32x cubed minus 6x squared, and then just throw the dx right on the end. Okay, so there's one little shortcut. Now here's another thing I like to do when I go about these problems. Some people like to always solve for dx, by dividing by this quantity, and you'll have du over that quantity, and you put it here, and then most of it's going to drop out. I like to start to think ahead, what am I going to be left with? And this is personal preference, so it's totally up to you. So I like to kind of, I guess, try to make this side, say, 16x cubed minus 3x squared dx. That's what I'm trying to get to cancel, right? So if you can think about that, that would be accomplished basically just by taking half of this expression right here. So in other words, if I divided both sides by 2, I would have 1/2 du on the left side, and then I'll have 16x cubed minus 3x squared dx. And there you go. Now that stuff, all of that stuff that I'm looking to cancel out, is equal to 1/2 du. And that's what you would be left with if you did the whole solve for dx, plug in, everything would cancel except a 1/2. So that I'm going to take these two expressions out and replace with 1/2 du. And there we go. Now it's all in terms of u. Again, that 1/2 could be factored out in front, or it could be, put right here if you prefer it on the inside. Doesn't really matter at that point. That's a constant multiple, can always be factored out or distributed in. And to integrate this, I still like to take this step and rewrite this as u to the 1/5. And now we use that power rule, and you see it's really just a simpler thing I'm taking the antiderivative of. So u to the 1/5, we add 1 to that exponent, and you will get 6/5, and now you divide by 6/5, which means you're really multiplying by 5/6. And when I multiply that 1/2 that's out in front by 5/6, I get 5/12 plus c on the end. And now just replace, substitute back in. U was standing in place of 8x to the 4th minus 2x cubed. And so there we go. Take the derivative if you want to see it all play out, how that 5/12 will cancel and get down to having that original integrand there that you started with. There you go. There's a second example. So I took a couple little shortcuts, and you'll see how when you get good with these, they can go a little quicker than that first one I did. But hey, if you're not comfortable doing that, some of those little tips, hang on, do a little bit, take the extra step or two, and then when you get good, maybe you start to take some shortcuts. So next problem here, again, you've got maybe two kind of thoughts on trying to integrate this, and hopefully this just appears to you like, hey, this is not something normal that I used to integrate. It's a big, ugly fraction. And you might be thinking, am I trying to do a quotient rule in reverse? And no, the reason you have this quotient there is it's probably just the result of a chain rule. And so what was the inner expression that was causing that chain rule? The inside of that square root. So I'm going to let u be 4x cubed minus 6x, right? And so here's where I'm at. And eventually I start skipping this step too. I don't always take the step where I rewrite with just that u in place. I'll start skipping to the next step, soon enough with everything substituted in. But it's kind of nice at this point to see that's the stuff you've got to now get rid of. All that has to be changed over to a u expression. And so you can kind of see, if you start to think ahead, the next step is the key of what tells you if you've picked a good u value or if this is going to work, is when you do the derivative of it, when you do your du. So du is going to be 12x squared minus 6 dx. I just took the derivative of, with respect to x, so you throw the dx on that side, and you see there's your dx, and you see you essentially have this right here. You have 12x squared minus 6 dx, and here you have 24x squared minus 12. Whenever you basically have your derivative there, with the exception of maybe a constant multiple, you did a good job. So if I wanted to basically make this side, say, 24x squared minus 12, what do I need to do? Basically just multiply both sides by 2, right? That's your goal. So if I were to take out all of that stuff, I'm just going to replace it with 2 du. So this time, you can put the 2 out in front again, or you can, leave it on top. I just left it on top because sometimes you'll do that. No big deal. And now we integrate. So we have 2, and it's over root u, so that's really 2u to the negative 1/2, right? We bring that up, rewrite it with a positive exponent, and now add 1 to the exponent, divide by 1/2, which is going to make 4 out in front, plus c, and now switch back. We were just letting u stand in place, so if you like to use square root instead of the 1/2 power, doesn't matter. But u is standing in place for 4x cubed minus 6x. And there you go. So again, just to reiterate, to emphasize here, if this step right here, you don't like doing that doesn't feel quite right to you, where you are trying to make one side of your equation say what you're trying to cancel out. That's my approach, when you get the hang of it. If you don't feel comfortable with that, after you do your du step, just solve for dx by dividing by that quantity, and then put that in place of your dx. And you should see everything would cancel out except for a multiple of 2. So you'll be left with the same thing. I find this to be just like one or two steps faster. And maybe, I don't know, maybe the thinking of it, I kind of like thinking ahead like that, rather than just mindlessly kind of plugging in and hoping that the cancellation happens. So, all right. Well, those are 3 examples there. Hopefully they help out. If you have any questions, just feel free to ask.